When burying conduit containing communications and power, several specifications regarding depth, width, and shared trench usage must be considered. Let's discuss the depth requirements firstly. For power conduits, primary lines should be buried at a depth of 18 to 30 inches, while secondary lines should be buried at 12 to 24 inches. As for communication conduits, telephone and data lines should be buried at 18 to 30 inches, and fiber optic lines at 24 to 36 inches. The width of the trench should be wide enough to accommodate the conduit and any protective bedding material, typically ranging from 12 to 24 inches or as required by local codes. Now let's address whether power and communications conduits can share the same trench. Yes, they can, but certain requirements must be met. There must be at least 12 inches of vertical separation between power and communications conduits. If vertical separation is not possible, conduits must be separated by at least 24 inches horizontally. Considering conduit types, power conduits must be rigid or intermediate grade conduit, while communications conduits can be flexible or rigid. All electrical work must comply with the National Electrical Code, or NEC, or local electrical codes. Additional considerations include bedding, where conduits should be bedded in sand, gravel, or other approved material. A warning tape should be placed above the conduits to indicate their presence. Conduit installation should be inspected by a qualified electrician or communications technician. Trench should be backfilled with soil or other approved material and compacted to ensure stability. Remember that these specifications may vary depending on local building codes and soil conditions. Consulting with local authorities and obtaining permits before burying conduit is always advisable. When it comes to electrical safety in buried conduit systems, maintaining proper separation between power and communication lines is crucial. The 12-inch vertical or 24-inch horizontal separation minimizes the risk of electrical interference or accidental contact. Using the correct type of conduit, such as rigid or intermediate grade for power lines, provides necessary protection against physical damage and electrical hazards. Adhering to the National Electrical Code, or NEC, ensures that all installations meet the required safety standards. Proper bedding with materials like sand or gravel prevents damage to the conduits from rocks or other debris. Marker tape serves as a visual warning to prevent accidental digging or damage during future excavation work. Thorough inspections by qualified professionals ensure that the installation meets all safety requirements. Finally, proper backfilling and compaction provide stability and prevent settling, which could damage the conduits over time. In the context of electrical conduit installation, understanding the difference between rigid and flexible conduits is important. Rigid metal conduit, or RMC, is a thick-walled threaded tubing typically made of galvanized steel, stainless steel, or aluminum. It provides excellent mechanical protection and can be used in exposed or concealed locations, both indoors and outdoors. RMC is suitable for direct burial and can also serve as an equipment grounding conductor. Intermediate metal conduit, or IMC, is a thinner-walled threaded tubing than RMC, also typically made of galvanized steel. It offers similar protection to RMC but is lighter and easier to work with. IMC is also suitable for direct burial and can be used as an equipment grounding conductor. Electrical metallic tubing, or AMT, is a thin-walled unthreaded tubing typically made of galvanized steel or aluminum. It is lighter and easier to bend than RMC or IMC, but it provides less mechanical protection. EMT is generally used in concealed locations indoors, but can be used outdoors with appropriate fittings. Flexible metal conduit, or FMC, is a spiral wound flexible tubing typically made of steel or aluminum. It is used to provide flexibility in conduit runs, especially in tight spaces or where vibration is a concern. FMC does not provide as much mechanical protection as rigid conduits and is generally not suitable for direct burial. Liquid-tight flexible metal conduit, or LFMC, is a flexible metal conduit covered with a waterproof plastic coating. It is used in wet or corrosive environments where flexibility is needed. LFMC provides good mechanical protection and is suitable for direct burial with appropriate fittings. Electrical non-metallic tubing, or ENT, is a flexible corrugated plastic tubing. It is lightweight, easy to install, and resistant to corrosion. E&T is typically used in concealed locations within walls, floors, and ceilings. It is not suitable for direct burial or exposed locations where it could be subject to physical damage. High-density polyethylene, or HDPE, conduit is a flexible plastic conduit often used for underground applications, including direct burial. It is durable, corrosion-resistant, and can be manufactured in long continuous lengths, reducing the number of joints required. When selecting conduit, consider the environmental conditions, the degree of mechanical protection required, and any applicable codes or regulations. The National Electrical Code, or NEC, provides detailed guidelines for conduit selection and installation in Chapter 3. Section 300.5 of the NEC specifies the minimum burial depths for electrical conduits and cables, depending on the voltage, location, and type of wiring method. Section 310.15 provides guidelines for determining the allowable ampacity of conductors in conduits, taking into account factors such as the ambient temperature, the number of conductors in the conduit, and the type of insulation. Always consult the latest edition of the NEC and local codes for specific requirements in area. When planning an underground conduit installation, proper site preparation is essential. Firstly, conduct a thorough survey of the area to identify any existing underground utilities, such as gas lines, water pipes, and communication cables. Contact the local utility companies or use a one-call service to locate and mark these utilities before digging. Secondly, determine the route of the conduit run, taking into account any obstacles, such as trees, rocks, or buildings. Choose a route that minimizes the number of bends and avoids areas where the conduit could be subject to physical damage. Thirdly, excavate the trench to the required depth and width, following the guidelines for burial depths. Make sure the trench is wide enough to accommodate the conduit and any necessary bedding material. Fourthly, prepare the bedding material, such as sand or gravel, and place it in the bottom of the trench. The bedding material should be evenly distributed and compacted to provide a stable base for the conduit. Fifthly, install the conduit in the trench, making sure it is properly aligned and supported. Use appropriate fittings and connectors to join sections of conduit and to make connections to equipment. Sixthly, backfill the trench with soil or other approved material, compacting it in layers to ensure stability. Avoid using large rocks or debris that could damage the conduit. Seventhly, install marker tape or other warning devices above the conduit to indicate its presence. The marker tape should be buried a few inches below the surface and should be easily visible during future excavation work. Finally, conduct a thorough inspection of the installation to ensure that it meets all applicable codes and regulations. Have the installation inspected by a qualified electrician or inspector before energizing the circuit. For example, consider a scenario where an electrician needs to install a 240-volt circuit to a detached garage. The electrician plans to bury the conduit underground to protect the wiring and maintain a neat appearance. The electrician must firstly determine the correct type of conduit to use. Since the conduit will be buried, the electrician could use rigid metal conduit, or RMC, intermediate metal conduit, or IMC, or rigid non-metallic conduit, or PVC. RMC and IMC provide excellent mechanical protection, while PVC is corrosion resistant. Secondly, the electrician must determine the minimum burial depth required. According to the National Electrical Code, or NEC, Table 300.50, a 240-volt circuit requires a minimum burial depth of 18 inches for RMC or IMC and 12 inches for PVC. Thirdly, the electrician must prepare the trench. The trench should be at least 6 inches wide to accommodate the conduit and bedding material. The electrician should also remove any rocks or debris from the trench to prevent damage to the conduit. Fourthly, the electrician must install the conduit in the trench. The conduit should be laid on a bed of sand or gravel to protect it from sharp objects. The electrician should also use proper fittings to connect the conduit to the garage and the main panel. Fifthly, the electrician must backfill the trench with soil. The soil should be compacted in layers to prevent settling. The electrician should also install a warning tape above the conduit to alert future excavators. Finally, the electrician must have the installation inspected by a qualified inspector. The inspector will check the depth of the burial, the type of conduit used, and the quality of the workmanship. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines for electrical installations. It is updated every 3 years to reflect changes in technology and best practices. Article 300 of the NEC covers general requirements for wiring methods and materials. It includes provisions for the use of conduits, cables, and other wiring methods in various applications. Article 310 of the NEC covers conductors for general wiring. It includes tables that specify the allowable ampacities of conductors based on their size, insulation type, and ambient temperature. Article 314 of the NEC covers outlet boxes, device boxes, and pull boxes. It includes requirements for the size and installation of these boxes to ensure that they can safely accommodate the conductors and devices. Article 320 of the NEC covers armored cable, or AC. It includes requirements for the construction, installation, and support of AC cable. Article 330 of the NEC covers metal-clad cable, or MC. It includes requirements for the construction, installation, and support of MC cable. Article 334 of the NEC covers non-metallic sheathed cable, or NM. It includes requirements for the construction, installation, and support of NM cable. Article 340 of the NEC covers underground feeder and branch circuit cable, or UF. It includes requirements for the construction, installation, and support of UF cable. Article 344 of the NEC covers rigid metal conduit, or RMC. It includes requirements for the construction, installation, and support of RMC. Article 348 of the NEC covers intermediate metal conduit, or IMC. It includes requirements for the construction, installation, and support of IMC. Article 352 of the NEC covers rigid polyvinyl chloride conduit, or PVC. It includes requirements for the construction, installation, and support of PVC conduit. Article 356 of the NEC covers liquid-type flexible non-metallic conduit, or LFNC. It includes requirements for the construction, installation, and support of LFNC. Article 358 of the NEC covers electrical metallic tubing, or EMT. It includes requirements for the construction, installation, and support of EMT. Article 362 of the NEC covers electrical nonmetallic tubing, or ENT. It includes requirements for the construction, installation, and support of ENT. Proper grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, causing the overcurrent protective device, such as a circuit breaker or fuse, to trip and to energize the circuit. Bonding connects all metal parts of the electrical system together, creating a low impedance path for fault current. The National Electrical Code, or NEC, Article 250, covers grounding and bonding requirements. It specifies the types of grounding and bonding conductors that must be used, as well as the methods for connecting them. The grounding electrode system typically consists of a ground rod, a ground ring, or a metal water pipe that is in direct contact with the earth for at least 10 feet. The grounding electrode conductor connects the grounding electrode system to the equipment grounding bus in the electrical panel. The equipment grounding conductor provides a path for fault current from the metal parts of equipment back to the equipment grounding bus. Bonding jumpers are used to connect metal enclosures such as electrical boxes and conduit to the equipment grounding conductor. Surge protection devices, or SPDs, protect electrical equipment from voltage surges caused by lightning, power line switching, or other disturbances. SPD divert the surge current to ground, preventing it from damaging sensitive electronic components. The National Electrical Code, or NEC, Article 285, covers surge protection devices. It specifies the types of SPD that must be used in various applications, as well as the methods for installing them. SPD are typically installed at the service entrance, as well as at branch circuits that serve sensitive electronic equipment. Regular maintenance and inspection of electrical systems are essential for ensuring their continued safety and reliability. Maintenance tasks include tightening connections, inspecting wiring for damage, and testing of current protective devices. Inspections should be performed by qualified electricians or inspectors to identify any potential hazards or code violations. The National Electrical Code, or NEC, Article 110, covers requirements for electrical safety. It specifies the types of personal protective equipment, or PPE, that must be used when working on electrical equipment, as well as the procedures for de-energizing circuits and testing for voltage. Lockout-tagout procedures are used to prevent accidental energization of circuits during maintenance or repair work. These procedures involve placing a lock and tag on the circuit breaker or disconnect switch to indicate that the circuit is being worked on. Before beginning any electrical work, it is important to identify all potential hazards and take steps to mitigate them. Hazards include shock, arc flash, and electrocution. Mitigation measures include wearing appropriate PPE, de-energizing circuits, and using insulated tools. Safety training is essential for all electrical workers. Training should cover topics such as electrical safety, grounding and bonding, overcurrent protection, and lockout-tagout procedures. In addition to the National Electrical Code, or NEC, there are other standards and regulations that may apply to electrical installations. These include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, the National Fire Protection Association, or NFPA, and Underwriters Laboratories, or AL. Local codes and regulations may also impose additional requirements. It is important to be familiar with all applicable standards and regulations before beginning any electrical work. This is especially important when showering a trench because of the close proximity of high and low voltage systems.